All right, welcome everyone. My name is Philip, yes, and I'm here currently in Hamburg. Today, I'm happy to give you an introduction and overview about the Parthenon AMR framework. And I first want to highlight that this is by a large margin, a very large collaborative effort. So this is by no means like my work. So a lot of people have been involved over the years. So this is like really a community effort in order to get everything working, including the Kokkos community. So before we jump in terms of what block-structured adaptive mesh refinement is or why we actually went in that direction, let's first take a step back and look at how the high-performance computing landscape changed over the past years, because that eventually led to like all the development efforts that went into this. Because we've been working on this more or less for like starting around 2017-ish. And so our original motivation was that like still during the petascale era, it was already clear that like GPUs are becoming more and more prevalent. And what you can see here is like a rough timeline of systems on the top 500 and their special programming models, where like when I say like there's no special programming model, these are typically like GPU systems that didn't require any like special sauce to apart from like potentially changing the compiler or a couple of flags. But then the like very first big impact was probably Summit in 2018, that where the majority of the compute power was powered by or provided by NVIDIA GPUs. And back then it was already clear that the future is going to go in many directions. This means like GPUs from many vendors, but also potentially not only GPUs, but other kind of hardware. And so having this in mind, which was actually like conveyed during one of the like Argonne training programs on extreme scale computing, which I can highly recommend. We were back then also introduced to Kokkos and overall like the concept of performance portability. Because in general, like the this plan ahead was having multiple implications. From a computational point of view, the like classical multi-core architecture went to like many cores, including like several thousands of cores per individual device nowadays, which came with like diverse hardware and programming models, as I mentioned before. And so like the traditional approach to like just recompile your code, run it on more nodes, and be happy just didn't work. At the same time, modern scientific codes are becoming more and more complex. So porting your code from one architecture to the other is definitely not sustainable. And then also, like from a broader point of view, from a societal point of view, HPC uses large amounts of resources, energy in, heat out, CO2 out. And so for the kind of hardware that is available, we do want to make efficient and effective use of whatever is available in these capabilities. So the bottom line is like on the right-hand side is kind of like a small supercomputer model built on Raspberry Pis. Like actual supercomputers are much more complex and we need performance portability. So in the broad sense, like any single source code that makes efficient use of the hardware architecture, whatever that may be. Though this is probably preaching to the choir here because this is the Kokkos Tea time. So let's jump in. Once we basically were convinced that we should go in that direction, we took coming from the astrophysical community, we took a widely used code called Athena++ that was running on CPUs only. And the major point was the code was already highly optimized for vectorization. So and many of the expensive parts in that code were like tightly nested loops over KJI indices, where the innermost loop got a progma for OpenMP SIMD so that the compiler at least tries a little bit harder to vectorize this on the than modern CPUs. So we took that code and put that together using Kokkos. So basically translated the triple nested for loops into like Kokkos parallel fors using all kind of execution policies. So the right-hand side should look very familiar for people already working with Kokkos. So this is an example for a hierarchical parallelism where we have full control over like how we want to separate individual indices into blocks of threads. So in teams, how these threads in the individual team should handle another set of separate indices up to the fine-grained, most fine-grained detail on how to potentially vectorize over just another index, so the I index here. In practice, for people who are very used to this, this may look straightforward. For people who are mostly concerned about applications, for example, in physics, that may look a little bit scary. So therefore, we did introduce in like our original test case, but it's also still around in the current version of Parthenon and derived codes, an intermediate abstraction layer where we basically introduced another power 4, which now may stand for Parthenon 4. But that abstracts away the entire Kokkos, the Kokkos template or the Kokkos parallel force. So that we again now have a kind of simple interface so that with the goal that like simple things stay simple. So for application developers, they can focus on their application and don't need, let's say, expert knowledge around how to handle all the nested parallelism. So we did this like back in 17 or 18. The resulting code we called K-Athena for Kokkos and Athena. And we were back then able to run at 76 parallel efficiency on all of Summit. So that was already like a good path forward. So one part of why this worked was because we had that intermediate abstraction layer, or like one way why this still worked also on CPUs was this intermediate abstraction layer. And as an example why like the Kokkos execution policies can be a little bit tricky is shown in these plots here. So what you can see here is on the y-axis, the wall time, so the amount of time spent relative to the most expensive kernel. So for our classical finite volume hydrodynamics or magnetohydrodynamics codes, the Riemann solve, so calculating the fluxes, is often like the most expensive operation. And so it's normalized to 1 here. And then we tried on the x-axis, you see various other kernels ordered by like typical compute costs. And so we then tried both on GPUs on the left and on CPUs on the right-hand side, various execution policies. And so what in the end turned out that, for example, on GPUs, using a flat 1D range was always the fastest case compared to trying like a team policy, so nested nested hierarchical parallelism, or using MD ranges. Whereas on the CPU, the performance in general with Kokkos, depending on the kernel, was either identical, or you can see here there's a new line, which is the red line, which is the plain SIMD4, where we more or less threw out Kokkos entirely. Because when we learned initially, compilers have like quite a bit of challenges to properly vectorize with the Kokkos templates surrounding the kernels. So once we went like replacing our like the actual loop pattern inside our abstraction layer to a plain 4-4 SIMD4 loop, we got back to like the original performance. And that is today still the case. So in some of our downstream codes, we actually manually extract pointers from the Kokkos views that are then specifically passed to the innermost for in a hierarchical loop, because that allows more compilers to efficiently vectorize the code. Caveat, well, no, disclaimer here, we haven't redone this test like with the latest version of Kokkos with all the improvements that went into the MD range. So this is like kind of the motivation why we initially introduced that intermediate abstraction layer and still like carry it around. And so now it's kind of like a compile time argument depending on the machine we're going for. We set like the default execution policies and rules at that level specifically to a certain machine or architecture. So the original code that we had, so Cathena, was only doing static uniform meshes, and at the same time, so that basically limited our the kind of applications we had in mind. And so the next step, if you want to go beyond uniform goods, you introduce mesh refinement or adaptive mesh refinement. And the main idea is on the right-hand side, you can see an animation of a like canonical blast wave. So you have an overpressurized region in the center that goes out. The key point here is that each square, so each block in this case, has the same identical size and the same in the sense of having the same number of cells. And then if we are interested, we can increase the resolution by in 2D, like splitting one block into 4 blocks and so forth. And here what you can see is that you're tracking the interface with like a finer grid. And so therefore, we can increase our spatial resolution in the regions of interest and therefore overall make the computation more efficient because we don't have to run the entire simulation at like the highest resolution. Conceptually, in the way we approached or like used the block structure, adaptive mesh refinement, all the blocks are logically independent but identical. So they all have the same size. And they only communicate with their neighbors through like a layer of buffer zones around the active cells. So therefore, when you write a compute kernel, you only need to tell each block what to do inside that block. And then everything about how the information progresses through the domain is always done through these ghost layer communication. One important point here to mention is that the block size is very important for several reasons. So first of all, for like large active zones and you are basically can have a very thin layer of ghost zones around, but also that would result in very like in hierarchies that cannot be very shallow. So you would always refine a large chunk of the volume if you have 2 large blocks. On the other hand, if you start with like very small base blocks, then you can have a much sharper transition between individual levels. But on the other hand, you have many, many, many more blocks that increase the total amount of communication that needs to be done, and also the ratio of like your ghost zone layer to your active cell layer gets worse. So therefore, there's already kind of like a trade-off in terms of what can be done. So it's like, well, not what can be done, but it's a highly problem-dependent choice on like which block size is good for a certain kind of target application. So with the Cathena being originally like on uniform grids, kind of like a proof of concept, people at Los Alamos were working at the same time also looking into Athena++, so the basis for Cathena, for using the adaptive mesh refinement from the framework. And eventually we all pooled resources, and now what then became Parthenon. So this is now a larger collaboration. So we have more than 20 people who already contributed to the code base, with the overall goal that we want to hide the complexity of doing device-accelerated adaptive mesh refinement. And this effort was started like right before Corona happened. So we had the first official meeting in January 2020 and have been actively developing the code ever since. One of the key design decisions that went into Parthenon is that it is like device first or device resident, depending on your favorite wording, which means all our data is always allocated only on device, including communication between individual rings. So we never copy data to the host unless we're doing I/O, and potentially even right now working also on like directly doing this from the GPUs directly. But in principle, there is no explicit data movement between host and device, because in the past, this turned out to be like a bottleneck in terms of like getting the most compute out of like your available hardware. And then another key design decision is that we are working quite hard to be smart about how we logically pack data or fuse kernels, and I will go into detail, go into more detail how that works and why we have to do it in the following slide. On top of these performance design decisions, Parthenon by now has like a lot of advanced features. So we have abstract data containers where we can have all kind of variable types: cell-centered, face-centered, edge-centered, node-centered. With fluxes, we have a packaging system so that even between downstream codes, if you've been writing your physics algorithm or implemented your physics algorithm as a package, it can be easily transferred across codes. We have task-based parallelism, so all the like the main loop is going through a task, a directed cyclic graph that is constructed, which also allows like iterative task for algorithms that require like an iterative solve. We do have sparse variables that I will touch in a second in more detail, where we only have to, where we can run a simulation where not all the data is allocated everywhere. We do have support for particles and integrated solvers like multigrid. And so it's like a large selection of features available that is the basis or are the basis for multiple downstream codes, where not all downstream codes always need all the features. But given that we are like a large community developing in sync, whenever there's like a new feature being added, we make sure that the interfaces are implemented in a way that they can eventually be used by all downstream codes, like in principle, very straightforward manner. So I briefly touched on the packing. So why do we need packing or kernel fusing? So the original, say, Athena++ approach for handling ghost zone communication, which we identified as one of the bottlenecks initially, is illustrated on the right-hand side, where over time we would launch a kernel on the host in red, then we would fill the buffer filling kernel, so like filling the ghost zones for the communication buffer, would then run on device. Then we would have a barrier, and then we would have the MPI call to do the asynchronous exchange of the ghost data with like other rings. And in the original version, this was just like a very large for loop where each individual buffer was filled by a separate kernel. We then noticed that the amount of kernels, which can easily reach like 100,000 buffers per individual device, can introduce a significant overhead, because there is about a 5 microsecond launch latency, which, as we learned, is, at least on NVIDIA, inherently serial. So we initially tried to do multi-threading on launching kernels, only then to learn that we are again basically doing serial kernel launches. And so the first attempt that we did was to start packing the buffers, so all the communication buffer, in a single device kernel. So now in the center on the right-hand side, we only do have a single kernel launch, and then pack all the buffers on block 1. Then we start all the MPI communication. Then we launch the kernel for the second block, again, all the communication buffers, and so forth. And then again, this didn't quite get to where we wanted to be. And so in the end, we now have the possibility to not only pack the buffers of all of each block, but also the buffers of all blocks into potentially even a single kernel, and therefore drastically reduce the total time spent, like in terms of overhead by launching kernels. And this is not only relevant for buffer communication, but for example, if we want to use a depth mesh refinement with very small blocks, say like 16 cubed, we have only 4,000 cells in that block for like active work. And with now more than like several thousand of cores per device, there's just not enough work so that the even our most expensive physics kernel is in principle taking longer than it would require to launch the kernel itself. So therefore, in general, we have to combine the work into fewer kernels. As an example, on the right-hand side, you can now see a performance measurement where we have a fixed mesh both on the CPU and on a GPU, where the blue dashed line is the GPU version. We have a fixed mesh. We just over-decompose the mesh into more and more blocks. So initially, we start with like a single block covering the entire domain, going all the way up to 4,000 blocks covering the same domain. And what you can see is that on the CPU, the overhead is about a factor of 2 to 3, which is basically expected because you now have the additional overhead to manage like 4,000 blocks on the host, like independent of the amount of compute you're doing. On the GPU, the initial overhead of this decomposition was almost a factor of 100. So like nowhere that would get you any performance. So when we then introduced to pack the buffers in the individual kernels, which is now like the dashed dotted line, we were able to push down the overhead to about a factor of 12. So better, but still not great. Lastly, when we started to pack buffers and blocks, we were actually able to push the overhead down to the same level that we had that we were seeing on the CPUs. So basically, that allowed us that we can now even run large simulations with very small blocks on GPUs. So where did this get us? So we did scaling tests on various architectures. So on the right-hand side is a weak scaling performance plot where we have on the x-axis the number of nodes, starting from one node going all the way up to almost like 10,000 nodes. The bottom panel shows the parallel efficiency. So how much do we lose compared to like running on a single node due to the overhead of doing communication across multiple nodes. And on the top, you have the raw performance per node in cell updates per second. And you can already see the clustering. All the CPUs in these systems are like the bottom lines, and the GPUs are at least an order of magnitude faster. So typically, for many codes, we do see speed ups of like about 4 to 5x per GPU over a dual socket system. And at the very largest scale, so the pink line here, we were able to go from a single node to 9,400 nodes on Frontier, keeping the parallel efficiency at 92%. And so this demonstrated that we can now actually do performance portable GPU accelerated AMR. And these nice results on Frontier also basically led to Parthenon being one of the codes that are now regularly used for machine regression testing on like performance regression testing on Frontier. So are all problems solved by just packing everything super dense in single kernels? Of course not. One new issue now shows up by packing things into very large individual logical blocks. So what you can see here is the performance for each individual cycle. So we ran like a test simulation that was fixed on 1,000 nodes with a fixed amount of work for like 50 cycles and measured the performance for each individual cycle. The only thing that varies between the 4 panels that you can see here is the block sizes and pack sizes. So block size here actually means like the logical block size, and the pack size is how many blocks we put into a logical pack. So on the left-hand side, we start with a single block of 512 cubed per GPU. And then on the right-hand side, the other extreme case is where we have blocks of 128 cubed, but 64 of those on each GPU. And in between, there are intermediate block sizes with like an intermediate number of packs. And what you're seeing here is that the raw performance is definitely good if we have the least amount of decomposition. But the more blocks we have, so smaller and smaller blocks, which we do need for AMR, we now see a large scatter in performance, where like the cycle or the performance for individual cycles may drop by a factor of 4. And that the problem that we identified is that if there is too many, based on the current design, if there is too much work for the buffer filling happening in one go, then we are flooding the interconnect between the nodes with too many messages at the same time, leading to congestion and therefore resulting in very like erratic performance numbers. Again, this was an issue identified, which is now addressed. So now we do have the possibility to like coalesce messages between ranks. So in the original approach, we would be sending for each buffer, so for each ghost zone, between each 2 blocks, we would send 1 message. So if we have many blocks per rank, even between same ranks, many different blocks would exchange many different messages. Now we have support for coalesced messages. So therefore, we can pool all the messages between ranks into fewer messages, where fewer means it's a runtime configurable parameter. And also, we now have support for do index splitting, because if we're working with hierarchical parallelism, we also need to ensure that we have enough buffers to be handled by the individual teams, because originally we're potentially launching too few teams to even get all compute units involved in the buffer filling kernel. And so that allowed us to increase the occupancy on the devices. And so there's always like a trade-off in terms of like your target simulation size, target block size, and the like subtleties of the machine and the interconnect. So one feature that is like specific to, I think, pretty much specific to Parthenon, and is allowing for a great deal of flexibility is, as I mentioned, like the packing of variables in blocks. And so this will be like the only technical code slide or code path. The main idea here is that as I mentioned, the individual blocks are logically independent. And so each variable or each quantity that we have is also tied to an individual block. So when we combine a Kokkos view with some metadata, metadata in our case could, for example, be whether it's an cell-centered or an edge-centered or face-centered field, or whether it's sparse, that defines a variable. We then can pool multiple variables into what we call mesh block data. So this is all the variables tied to a specific mesh block. And then one level up in the hierarchy, if we have mesh block data across multiple blocks so that we can like work on them in individual kernels, we end up with something that we refer to mesh data. And then at the highest level, when we have a pack, this is an arbitrary collection of variables across blocks. And in the jargon of Kokkos, this is a view of you, potentially of views, that everyone tells you don't do. We're still doing it. There's a caveat here. I'll come to that in the very end. But kind of like this is the approach we are currently doing, which is very powerful. And with the additional metadata allows for a lot of flexibility. So one nice feature that this allows is, or that we also have, is type-based variable namings. So you can create a variable that is referenced to by a C++ type. So in practice, then, if you're if you want to index, you don't have to work with like global indices and keeping track of which field in your view corresponds to which index, and if you recompile, that may or may not change. In Parthenon, you can actually use a specific type, or you can define a type, and then PKG here is a package. So this is kind of like our structures on how you can implement physics in like separate packages. On the bottom, you can see we now can add a field, or we can add a sparse pool where we add the specific type into our package registry. And when we want to access that kind of data in the kernel, we have a structure that is called like a pack descriptor, where we can now put in all the variable types we want. So these are like globally known and could also be abstract types. So for example, you can not only use variable names, but you can, for example, say, I want to have all the variables that are fluxes, or I want to have all the variables that are face-centered into like a single pack. And then as an additional argument, you pass in the mesh data object. So this carries all the blocks or like a subset of blocks that you want into that descriptor. Then you create a pack specifically tied to all the blocks inside that mesh data object. And now finally, if you want to execute your parallel region, the main abstraction consists of going over all the blocks in the pack. So this is the B index, then going over the KJI indices. And then inside the kernel itself, you can, for example, directly access the elements inside that view or inside that pack that eventually maps to a view via the type name. And if you have sparse variables, not all your indices may be populated because there is no data in certain indices. Then you can extract the actual indices inside that pack that are going to map to the underlying view, so that you can access these kind of sparse data. So what does sparse in this context actually mean? This is an example that you can see here. On the bottom left, or like it's an AMR simulation, you can see various block sizes. In the bottom left, you have the bulk density of this triple point flow. And the bulk density is composed by 3 different components. And the key part here is that all the white blocks in the 3 components, so top left, top right, and bottom right, the white blocks are not allocated at all. So there is no data here that needs to be carried around. And so we have various thresholds that you can enroll in, like how to allocate or deallocate data. And that allows you to do like simulations with many different, say, materials or properties that may only be present in some part of the domain, but not everywhere. And so you can skip all the computation, all the communication that results in also results in pretty large speedups. So conceptually, you can think about it if you have a table in a room. You don't want to have like your table field for the table allocated in the entire space, only to say in certain parts there is no table. But actually, we can get away by just keeping the table where it is and allocate data for the table on where the table is physically located. So, as I mentioned, there is quite a bit chunk or a good chunk of multiple downstream codes. I'm just going to mention a couple here. So Athena PK is our own astrophysical, like own the sense that like I'm using it myself with other people and developing this with other people. It's targeting astrophysical MHD and quite a few of turbulence simulations. There's Phoebus, developed as Los Alamos for doing GR MHD simulations, for example, for neutron star mergers. There's Calmer, which is used by the Event Horizon Telescope collaboration. So if you haven't heard about this, on the right-hand side, the image you may or may not have seen. It's the first kind of like direct image of a supermassive black hole, though direct is not entirely correct because the image had to be reconstructed from data, and the data was matched to various patterns that were, in this case, also simulated with Calmer that was based on Parthenon. Then there is Riot, which is in a Lanel internal code for multi-material physics, like the triple point simulation that I showed on the previous slide is from Riot. There is Artemis doing multi-fluid radiation hydro. There's a version of Flash that is based on Parthenon targeting fusion power. And we also have, as an introductory code, Parthenon Hydro, which is like plain just 1,000 lines of code that we use for like tutorials and teaching, and gets you like fully compressible Euler equations in with AMR support in very few lines, so like comparatively easily digestible. Another part to highlight is Parthenon does not only have like downstream applications that are developed in SIM, but also there's like an additional ecosystem around it. So there's, for example, Singularity EOS, which is like an equation of state microphysics library that can easily be attached or like included in various Parthenon codes. There's JBen to do Monte Carlo radiation transport. And many other like smaller code bases, and they're all kind of developed around the Parthenon interfaces. So there's a lot of like exchange between the individual code bases. So as an example, in Athena PK, when we needed particles, Artemis already had particles written up. And I was able to, like in a single day, to port the Artemis particle implementation to Athena PK, so that like at least the basic particles were at that point directly working immediately without me going into all the detailed like needing to reinvent the wheel. So personally, I'm mostly involved, apart from Parthenon, also like in the development of Athena PK. Which is also like an open source code. We are doing this for doing supernova remnants, cloud and winds. On the right-hand side, you can see a simulation with AMR, where we looked at how a galaxy falls into a galaxy cluster, which then leads into like stripping of gas from the galaxy, resulting in these extended tails. Technically, they're not supposed to exist by dynamical arguments. In practice, they're there. So we ran some simulations with AMR, and on the bottom you can see magnetic field lines that are draping around this galaxy, shielding it, and therefore aiding in the survival of that kind of galaxies. We're also running simulations with jets from active galactic galaxies. And also right now, one of the bigger efforts is magnetized turbulence, which is one of the first larger projects on Jupiter. So the first exascale machine in Europe, in Jülich. And that is one part in terms of like what we where we successfully more or less push the limits of what can actually be done. So there we are running a 4 trillion cell MHD turbulence simulations, doing like checkpoints, writing, restarting, where the total checkpoint size is like approaching 300 terabytes per individual checkpoint. Other things where Athena PK basically pushed the limits also of Parthenon is trying to run with like 26 cells of ghost layers, trying to find a sweet spot between communication and computation for iterative solves. And also like particles with up to 57 fields. And the beauty here of Parthenon was changing the number of ghost cells, changing the number of fields for each for the particles is basically a 2-line change, and everything else happened completely transparently to the downstream application. So therefore, or with that, I would like to conclude by saying that performance portable adaptive mesh refinement works in practice. Even though I've been told years ago that everyone knows you can't do it. Well, apparently you can do it. With the small caveat that it requires like non-trivial pooling of resources. And the pooling here refers to the packing, the coalescing of communication messages, so potentially tuning the loops to specific architecture. So there are some subtleties, but large and all, it works. And then also big shout out to Kokkos to enable this in first place, and especially like the Kokkos community who has been extremely supportive from the very beginning. So when we started with Athena, we went to one of the first Kokkos developer weeks, had someone sitting next to us for an entire week, and we had a good chunk of our code base working by the end of the week. So that's without that community support and effort, this would not have been possible. Some of the current challenges that we are facing is that we have quite a few kernels that have very high register pressure, and the kind of how we implemented the packing is resulting in additional register pressure because the packing infrastructure, once captured on device, requires additional memory that is currently leading to slowdowns that technically are not necessary. So we're in the process of addressing this. Similarly, memory pools, memory allocations are expensive. So for our buffers, we already have like a manual memory pool where we go and like use subviews to extract chunks. That comes with own challenges, especially when it comes to using these for COM buffers, which are very ugly, and I'm happy to talk about the more detail if people are interested. And then efficient vectorization is still an issue because compilers with like tightly or deeply nested complex loops are still not great in being as efficient in recognizing this could be vectorized than it may be visible by human eye. So lastly, I would like to close by saying that like we're an open and welcoming community. If you're interested in like trying any of the downstream codes, I think almost all of them are open source. But also we have a metrics chat, and we are pretty happy to help people getting up and started with like doing their own experiments based on Parthenon. And with that, I'm happy to take questions. Thank you.
Thank you very much, Philipp. Some impressive work and great presentation. I can imagine there is a lot of reaction questions. We have one in the chat by Harry. Harry, do you want to open your mic?
Yeah, you had mentioned about a custom implement parallel pattern called SIMD4, which gave very good performance. Is that described in? Yeah, they had also mentioned a TPDS paper. Is it described in that paper?
Yes, it's in that paper.
Okay.
But there's no magic here. The only thing that we actually do is we go back to this pattern. So this parallel 4 is being back translated to a plane 4, another plane 4, inserting a pragma OMP, SIMD, and then another plane 4.
Okay.
So at that point, we like the thing we only use from Kokkos at this level is the access to the views. Yeah.
Okay, thank you.
Any other question? Looks like everyone is shy. Well, in that case, I have a lot of them actually. I'm wondering, at the beginning, you mentioned some issues of performance portability with raw Kokkos usage. This is something that has kind of improved in the latest releases. So did you make a comparison for that, depending on the version of Kokkos?
We have not. So this is yeah. So I think with Kokkos 5.1, a lot of like improvements went into the MD range version. So it would be interesting to see how that impacts like the raw kernel performance. The more subtle thing that now recently came up is that with the change from the Kokkos view going from like the legacy implementation to the MD span-based implementation, the indices were changed to N64 types. And that had an additional impact on the register pressure. So some of our expensive kernels were actually 30% slower. And so, yeah, we are really currently looking into making our like the packing infrastructure more lightweight, so that only the information that is absolutely required goes on the device, because that is a pinpoint for us because it reduces the occupancy on the device.
Yeah, I think this point has been identified in many codes, and there is some work inside Kokkos about that. I had another question regarding it seems there are like a huge amount of AMR framework, especially on GPU, everyone is designing their own. So do you have like, not necessarily performance comparison, but what are the differences? Why choose Parthenon 1 to choose Parthenon compared to, I don't know, MREX or other frameworks?
Yeah, good question. So from a historical point of view, I guess if MREX would have been around earlier, we may have used MREX, because there's like a lot of like overlapping features, especially with MREX. But yeah, as I mentioned, like our development goes eventually back to like 2017, so that like grew historically. I think one of the nice features about Parthenon is the like, or potentially unique features is the sparse variables. So depending on your applications, some simulations will only be capable when using sparse variables. So I know that people at the lab are easily running simulations with like 50 plus materials, which are potentially only highly localized. And so if you have to allocate and handle all that data globally, then you will run into troubles by running out of resources fairly quickly. And I think one of the big advantages of Parthenon is that many of the performance critical pieces are runtime parameters. Like, for example, you can say how many packs do you want per rank. You can say how many teams are supposed to handle each pack. And so therefore, there is a very fine-grained control on how to maximize performance across various machines, because like depending on the machine architecture and machine interconnect, this does matter significantly in terms of performance.
Thank you. Are there any other questions? Otherwise, I can keep going. Yeah, I saw a hand raised. Answer?
Sorry, my mic was closed. Can you hear me?
Yes.
Yes, we can.
Yeah, I have two questions, in fact. The first one was about, you talked at some point on the slide you just put a few minutes ago on manual extraction of pointers to leave it to compilers to do the SCMD stuff. Could you just go quickly through why wouldn't you? I mean, what do you have against Kokkos SIMD not doing this correctly for you?
We haven't tried Kokkos SIMD yet. Again, this goes back to the time when Kokkos SIMD was not around, and so a lot of like performance critical kernels were then developed in that way, and so I don't think there was an effort in trying to make this work with Kokkos SIMD. But I would have to defer that question. We are not doing this in our code, and also not doing this in Parthenon. So this is something done, for example, in the Riot code. Yeah.
Okay. Okay. Thank you. Just a second question, if I may, please. Again, quite at the beginning of your presentation, you said that nested hierarchical parallelism is quite complex to be used by physicists or like numerical analysts, I suppose, who want to use the code. And so you made something out to like the Par4. And just on slide 11, I think you put what you actually did to be able to, and all the caveats you've piled up to be able to do to get good performance and to pack everything correctly for your sparse variables. How does it? I'm just curious about how is it used by people who may have found the first one complex about this one. Does anyone complain?
So far, no one complained. And well, also based on my own experience, most of the time when I come across this, I will just copy and paste an existing kernel that has the same, say, like boilerplate for what I need. So therefore, I don't think the expert thing is such a big issue. It may just look intimidating at first, but yeah, so far no one has complained. Like the bigger advantage is that we do have, say, high level control at the library level on what good defaults are for users who say go to a new supercomputer, just want to compile the code and run. Then we can by that can set hopefully sensible defaults for that machine.
Okay, thank you very much. Very interesting for our users. Thanks for the talk.
Thank you very much. So I don't know if we'll have time for more questions, but in the meantime, I wanted to say to you all, thank you for attending, and see you for the next tea time. It will be in May, on the 20th of May, and Yuichi Hazahi will tell us about Kokkos FFT. So see you then, and I don't know, Philipp, if you have 1 or 2 more minutes for more questions.
I'm happy to stay around if people have questions. So one potential like comment on the FFT. So we are also like interfacing with like other libraries. So for the I/O that I mentioned, like writing 300 terabytes, we are using Adios 2 through the OpenPMD standard. For doing FFTs, we're interfacing with the Hefty library. So we all also trying to make these interfaces possible so that we don't want to reinvent the wheel where there's always like a good solution. So all the problems that we currently addressed were things where we didn't find a proper solution available that we can hook into.
So maybe one last question kind of related to that. You mentioned you work very closely with the Kokkos team, and you also interact with quite a lot of other libraries. And I was wondering, in terms of governance, basically. You seem to have quite a lot of developers. So have you set up some formal governance model? As you most likely know, Kokkos now has moved to HPSF. Is that something you also might want to do? Another option would actually be to join the Kokkos project itself. So I was wondering, what is the situation?
So at the last developer meeting, there was broad agreement to try to become part of the HPSF. Just for various reasons, it just didn't happen yet. So it's on our roadmap. We would like to be formalize our government, so we don't have like rules written in stone yet, because like it's most of these are people like we've been collaborating together with like for many years, with some people joining, some people leaving. But yeah, it's on the list of things on formalizing this and then trying to become part of the HPSF.
Okay, great news. Thank you. And if there are no more questions, I guess it's time to say see you next month for this next tea time about Kokkos FFT. Thank you very much again, Philipp, and see you next month.
Thanks, everyone. Bye.
Bye-bye.